So we've integrated. Let's now evaluate the limits. And simplify the expression and see, supposedly something's going to happen. Let's see what happens. So let's see. We know we have this right side equal to a sum from n equals 1 to infinity. And we had an over 2. We had pulled that out. Then we had a big bracket with a couple of integrals in it, which we'd evaluated. Yeah. Now we're just going to plug in L and 0. So it had two terms. One was L over n minus n star pi sine n minus n star pi x over L, and the other was the n plus n star version. So the first one, let's plug in L. Okay. The only place that the x showed up was inside the sign. So it's still L over n minus n star pi sine, and when we plug in L, we get n minus n star pi, because x goes to L and there was an L in the denominator and they go away. So it's just n minus n star pi. And then minus, we plug in 0 for the other limit, but it's sine of 0 because there's an x in here, so sine of 0 is 0. So the 0 limit gives us nothing, right? So here's where we plugged in L. So that was the first integrated term. And then minus, and now we do the second term, the n plus n star term, and it's got L over n plus n star pi. And it was also sine of, let's see, of n plus n star pi, and then x over L. Well, we're plugging in L for x, so L over L cancels. So this is n plus n star pi. And then when we plug in the 0 limit, we again get 0, because there's an x here, so sine of 0 is 0. So that's all for that limit. Now, we wanted to evaluate the limits and simplify, so let's see what we can pull out. We can pull out an L, an over L, or an times L, and we can pull out a pi, 2 pi. So let's do that. That's just 1, and get rid of the pi, get rid of the L, and that's just 1. And that's as far as we can go, because these are n minus n and these are n plus n. All right. So we did what Joe Fourier said to do. We multiplied by the nth harmonic and we integrated, and we still have infinite number of unknowns and one equation. So it doesn't seem to really help much. But there's one further thing we can do. You can realize, since we understand the difference between n and n star, that we actually, of all these infinite number of terms, there's really only two kinds of terms. All these terms can be grouped into two things. Usually, n does not equal n star. In fact, almost every time, right? So if we say we're doing this for the fifth harmonic, n equals 5, then when n equals 1, n does not equal 1 star. When n equals 2, it does not equal 1 star. 3 does not equal 1 star. 4 does not equal 1 star. For 5 it does, but then for 6, 7, 8, 9, 10, a million, n does not equal 1 star. Right? So for all the terms except 1, this is true. And then for once, for one term, once, n does equal 1 star. Okay? So let's see what this expression does under these two conditions. Maybe we can get rid of some terms. Okay, when n does not equal 1 star, that's some sort of an integer. Maybe it's negative, maybe it's positive, depends on who's bigger. It's usually going to be positive, because n goes to infinity. But anyway, that's just a number. And sine, and this is some sort of integer times pi. But sine of an integer times pi is always 0. So for all infinite terms, this is 0. So that's a good start. We just eliminated a chunk of this thing for a lot of the terms. Minus, n does not equal n star. Well, 1 over the sum of two integers, that's just some integer, and that's the sine of, again, an integer times pi. Sine of an integer times pi is 0. So this is the exciting part. We have eliminated infinite number of terms. We've eliminated all terms 0. All these terms equal 0. That's a big deal. It's as excited as I can get. So it looks like Fourier may be onto something here. Okay? But what if the thing he did made this term 0? So we need to save something. Right? I could have come up with a way to make the terms go away. Multiply both sides by 0. Hafner series. Right? Now, well, we need to do something more intelligent than that. So let's see what happened to n equals n star. Well, over here, if n equals n star, n plus n star is some integer. But wait, all these things are still going to be integers. So this is looking bad now. N plus n star is an integer. Sine of an integer times pi is always 0. Not good. And here, again, if n equals n star, n minus n star is 0, sine of 0 is what? 0. Everything appears to be 0. And just to rub it in your face, the denominator is even 0. That's just cruel, right? Everything turned out to be 0. But wait, is this 0? What is 0 over 0? Is 0 over 0 like 1, or is it 0, or is it infinity? I don't know what 0 over 0 is. Well, to figure out 0 over 0, it doesn't depend on the 0 and the 0. It depends on how you get to the 0 and the 0. Okay? So you got to use something called, I believe it's called L'Hôpital's rule. I always call it the hospital rule in my mind, so that makes me forget the right name and how to spell it. But I believe it's called L'Hôpital's rule. So if you have two functions and you're trying to evaluate them, in this case at 0, and you can write them as a ratio like that, then the limit as they go to 0, if they're both going to 0 together, the limit equals the same limit, the place where they go to 0 of their derivatives. Okay. So if you can find these functions and find that their derivatives don't go to 0, whatever ratio that makes is the same. And I can show you, it's easiest really to see it with an example. So say we have sine of x over x. Right? And if we plot sine of x over x, it kind of looks like this. So here's your sine function. And well, it comes down like that too. And if you plot y equals x, that's just a line. And it actually has the same slope of sine of x around the origin. They both have a slope of 1. So if you think about what is sine x over x here, well, it's some value, here it's some value, here it's some value. And here, it's pretty much the same value. It's close to 1. I've drawn them a little too overlapped here. It's close to 1. And the closer you get to 0, they really become the same value. So in the limit as you approach 0, this ratio really is 1. Okay? Well, the way you find that with L'Hôpital's rule is you just take the derivative of both. Sine x becomes cosine x. And the derivative of x is just 1. And that ratio evaluated at 0 is 1. So that's how you use this rule to find what something that turns into 0 over 0 really is. Okay? So maybe L'Hôpital will save us here. We can see, what do we have? Well, we have almost exactly the example I just gave you. We have sine of this thing going to 0 times pi over the thing going to 0, n minus n star. So we take the derivative of that, the derivative of sine of n minus n star pi with respect to n minus n star is pi times the cosine. So this is equal to pi times the cosine of n minus n star pi over, and the derivative of just, if this, we think of this as the independent variable n minus n star, is 1. And if you plug in 0 for your n minus n star, then cosine of 0 is 1, the whole thing is just pi. So this term, 0 over 0, in this case, is pi. It's not 0. Okay? So Fourier is a genius, because he did figure out that if you multiply by the nth harmonic and integrate, you reduce this infinite number of terms down to one term. And then you have one equation and one unknown, and you can solve for the ANs. This is why we've heard of Fourier series and not Hafner series.